Watch a complex 3D environment shift or a sprawling network map process traffic, and you are witnessing applied geometry. Underneath those complex visual outputs and analytical models, the computer only sees a basic flat grid of numbers. In computing mathematics, this grid is defined formally as a matrix, a rectangular arrangement of numerical data organized strictly into rows and columns. This diagram displays the standard mathematical notation used to classify this structure and define the total size of the grid. The variable m represents the total number of horizontal rows, and the variable n dictates the vertical columns. To control computer graphics, process massive datasets, or train neural networks, you must master the mechanics of this grid. A neural network is a computing model of interconnected nodes designed to recognize patterns in raw data. Matrices do not passively store data. They provide the computational framework for executing multidimensional operations. Before we can execute operations on matrices, we must classify them by their specific dimensional shapes. This animation shows one-dimensional structures. First, the row matrix contains strictly one horizontal row, followed by the column matrix, constrained to a single vertical column. When rows perfectly equal columns, we get a square matrix, the primary arena for complex graphical and data transformations. Conversely, the zero matrix is a grid where every single element evaluates to absolute zero, serving as a blank operational state. This diagram illustrates the identity matrix, denoted by I, the single most important square matrix in computer science. Its exact construction relies on a stark contrast, a main diagonal populated entirely by bright ones, running from top left to bottom right, heavily surrounded by non-diagonal zeros. The functional power of the identity matrix lies in its role as the equivalent of the number 1. Any dataset multiplied by it remains completely unchanged. Identifying these structural baselines is the strict prerequisite to safely combining and transforming datasets. Matrix addition and subtraction provide the simplest methods for merging two disparate data grids. This diagram illustrates the non-negotiable condition for these operations. Both matrices must have perfectly identical dimensions. The addition is strictly element-wise. The top left value adds exclusively to the top left value. The bottom right adds to the bottom right, outputting a structurally identical matrix. To uniformly scale an entire dataset, we use scalar multiplication. A scalar is a single independent real number used to denote magnitude, standing apart from structured grids. This animation demonstrates the operation. The scalar sitting outside the grid systematically multiplies against every individual element inside it. These arithmetic functions are intuitive and linear. They operate in sharp contrast to the highly specific mechanics required when matrices multiply directly against each other. Addition merges data. Matrix multiplication executes a systemic transformation, utilizing a completely different set of rules. Matrix multiplication is the standard mechanism for data transformation. It is the mathematical process used to rotate 3D graphics or apply weight values in neural networks. This visualizes the golden rule of dimensional compatibility. The number of columns in the first matrix must exactly equal the number of rows in the second. This general mathematical formula defines the operation, relying heavily on sequential summation rather than direct element-to-element matching. The operation calculates the dot product. The dot product is an algebraic function that multiplies matching entries from two sequences of numbers and sums the results. It maps horizontal rows from the first matrix against the vertical columns of the second. Through a worked example, we use matrix A and matrix B to generate a new matrix C. Step 1 isolates the first row of A and the first column of B, multiplying overlapping elements and summing the results to output 19, the new top left element. Processing the remaining rows and columns follows the exact same pattern, calculating out to 22, 43, and 50 to complete matrix C. This specific arithmetic sequence maps directly to computing hardware. A graphics processing unit, or GPU, is a highly specialized electronic circuit built precisely to execute millions of these exact row-by-column sums simultaneously. Matrix multiplication functions as the literal mechanism of spatial mapping and data transformation inside a computer system. If matrix multiplication transforms data into a new state, we face a fundamental computing problem. How do we reverse the process to retrieve the original data? This diagram shows a square matrix and its determinant formula, a scalar diagnostic tool predicting if mathematical reversal is possible. For this example, we calculate it by multiplying the main diagonal elements and subtracting the off-diagonal product, yielding a final determinant of 5. This resulting number delivers critical information regarding the internal geometry of the data, acting as a mandatory pass-or-fail system check. Before a computing system attempts to invert complex data, it must consult the determinant to verify that the data structure is still intact. Reversing a transformation requires the inverse matrix. Multiplying an original matrix by its inverse generates the identity matrix, effectively resetting the data back to its default state. This equation shows the formula to calculate the inverse of a 2x2 matrix, requiring internally swapping the elements and applying an external scalar multiplication. Applying this to our previous example, we generate a scalar fraction of 1/5, applying across the newly rearranged grid. However, the formula contains a severe structural vulnerability. The scalar fraction requires dividing the number 1 by the determinant. This establishes the absolute condition for invertibility. The determinant cannot equal 0. Reaching 0 is catastrophic. Dividing by 0 is mathematically undefined, creating what is known as a singular matrix, where the transformation becomes completely irreversible. A determinant of 0 indicates irreversible data collapse. The grid dimensions have flattened, and the original information is permanently lost. In the practical reality of programming, minor arithmetic errors compound into massive system failures. The most common programming blind spots include forcing matrix multiplication without validating dimensional constraints, or confusing the extraction of a scalar determinant with actual matrix multiplication. The singular matrix trap is equally dangerous. Attempting to reverse a massive dataset without first verifying the invertibility condition will crash an entire pipeline. This image displays a simple equation, AX equals B. In computing, solving complex linear systems relies entirely on these rules operating in harmony. That short equation encapsulates the workflow. Matrices structure the system, multiplication transforms it, and inverses solve it. From resolving local network nodes to calculating neural weights, the rules of the matrix grid dictate how modern software processes complex information.